I'm Marcus, as you probably gathered. I met Dave at a couple of conferences and he asked me to come along here this evening, so that's very nice of you. Thank you very much. I'm English, but I've lived in France for the last 10 years, partly because I prefer skiing over everything else. I'm a PHP coder, sysadmin, MySQL DBA, technical editor. I have a little two-person company that's actually based in the UK, and our main thing is an email marketing system called smartmessages.net. And as part of that, I've also ended up being the maintainer of PHP Mailer, so half the world has used my code at some point. And I also do some work for a pen testing agency in Amsterdam called Radically Open Security. So as part of hosting my own stuff and seeing the kind of things that other people do wrong and the mistakes that are made and how you can fix them, that's given me a fair amount of experience with TLS and how it all fits together and what you can do to make it work for you. So let's jump in. And what is it? Well, TLS is Transport Layer Security. It's a protocol, a specification, and it's really the new name for SSL, so the Secure Socket Layer. I say new, it's been called this since 1999, so it's actually really quite old. There have been a whole string of versions, SSL 2 and 3, there wasn't a version 1. TLS 1 came along in 99, 1.2 in 2008, and then 10 years later, 1.3. Now, 1.3 is actually quite significantly different to 1.2, and it had a very difficult gestation. There were lots of corporate interests trying to undermine some of its security things and make it weaker, and this took quite a lot of fighting in committees, but it did eventually make it out. Fundamentally, though, TLS is a set of standards for security and encryption. It's a whole set of things that fit together, and those things can act like a security layer that you can wrap around lots of higher level protocols, in particular HTTP, but also SMTP and all the usual suspects, including more recently things like DNS. Now, because it's just a specification, it's really up to people to actually implement that. And so, of course, there are a bunch of implementations that are in common use. The most common by far, OpenSSL. This is what you'll find in most Linux distributions. Now, the thing about OpenSSL is it's like TLS, it's been around for a very long time, and it ended up, it's an open source project, and it's essentially maintained by two people in their spare time. And a few years back, there was a major security hole found in OpenSSL called Heartbleed. And this led to a great deal more attention being paid to OpenSSL, and them suddenly realizing that half the internet is relying on the support of two people in their spare time. And they thought that this was really a bad idea. The people behind OpenBSD and SSH forked OpenSSL and cut out all of the old stuff and really cut it down enormously, but while maintaining most of its API. So for the most part, this thing called LibreSSL that came out of that project is mostly a drop-in replacement for OpenSSL. Boring SSL is Google's implementation of TLS, and it's a bit of a weird name, but the reason they called it that is because their idea was that you would never read any headlines about it. They don't want to have the kind of headlines that were associated with OpenSSL. So they do everything very, very strictly, very conservatively, and super secure as a result. So why do we want to use TLS? Well, it provides a security layer. And when we talk about security, we really mean three things. Confidentiality, making sure that only the people that we intend to see something can see something. Authenticity, making sure that the people who say that who they are actually those people, and that we can prove that we're who we are as well. And also integrity, making sure that the data hasn't been altered, tampered, faked, anything else, is entirely intact from one end to the other of its transfer. If you use TLS, you can get better performance on your web apps because you can use HTTP 2. Google will rank you higher. Well, this used to be a differentiator, but it's not really much of one anymore because pretty much everybody's using TLS these days. It's required for iOS apps and Android as well by now. Back in iOS 9, Apple introduced a thing called App Transport Security. Now, not only did this require TLS, but it actually required TLS with some actually fairly strict requirements that make it a lot more secure. Chrome 50 started disabling things if you weren't using encryption. So as of Chrome 50, which was a while ago now, geolocation is not available over unencrypted connections. But fundamentally, though, the whole point of using TLS is to keep the wicked witch out. We don't want the bad guys getting their hands on our stuff, pretending to be other people, twiddling with things, and just generally messing with our data. We want everything kept nice and secret. Thank you very much. So what's actually in it? Well, TLS is really a toolkit of a whole bunch of different things that all fit together. And so there's a whole bunch of things that go towards the overall specification. So there's a bunch of hash functions. Now, hash functions produce a fixed length digest from a variable length input. So whether you've got 1 byte or a terabyte of data, the output is going to be the same size. But more importantly, the tiniest change that you make in the input produces a very large change in the fixed size output. So if you change 1 byte in a 1 terabyte disk image and calculate the hash of it, you're going to get a completely different result. Not just a slightly different result, but a completely different one. At least a good hash function has that property. Hash functions allow you to prove integrity. Now, say, for example, you've got a terabyte disk image on 2 different servers, and you want to make sure that they're exactly the same. Naively, the way that you could compare them would be to copy the image from one to the other and then compare them byte for byte. But the problem with doing that is that what if it doesn't match? You don't know if the original file that you copied was bad or the transfer process corrupted it. You can't tell if the actual other one is good or not. And if they agree, then fine. But if they don't, then you can't be sure. The alternative way with a hash is you calculate the hash on both ends and compare the hashes. And the hashes are short enough that you can just look at them visually. It's a very quick and easy thing to do. And it means that you don't have to transfer the data. So hashes are great as an integrity check. There are a whole bunch of algorithms for that. MD5 and SHA1 are older. MD stands for Message Digest. SHA is the secure hash algorithm. And there's a more recent family, SHA2, which covers SHA 256, 384, and 512, which refer to their length in bits. Now, the next step up from a hash is a thing called a message authentication code. And this is really much like a hash, but instead of just taking the data as the input, it takes the data, but also a key. And this means that if you're going to recalculate the hash, not only do you need the data, but you also need the key. And this means that you have to have the same key as whoever created the MAC in the first place. And that means that you can prove authenticity, subject to the fact that you have to share the key. Well, that's a separate problem. And again, there are a whole bunch of algorithms for this, but for the most part, MAC algorithms are essentially hash functions with a wrapper around them. And the wrapper is called HMAC, which is hash-based message authentication code. So HMAC SHA-256 is a MAC code based on SHA-256. There are some dedicated MAC functions, in particular Poly1305 is a more recent addition to TLS, and that's in 1.3. Then we get to ciphers. Now, this is really what people think about when they talk about TLS. It's all about encryption. You want to make sure that you've got the confidentiality thing. Now, one of the things that when I was first getting into this that I hadn't really considered is that the encryption part is actually orthogonal to integrity and authenticity. Just because you've encrypted something and sent the message doesn't mean that that message hasn't been altered, faked, or tampered with in transit. And you can't tell. The encryption doesn't give you enough information by itself to guarantee those other properties. So you need to have a signature to go with it to prove that the message hasn't been tampered with. And you need authenticity to prove that it's actually who it says that it's from. And this is why you need all 3 of these things together. And that's what TLS does for you. Now, ciphers, the actual encryption algorithms, are based on mathematical problems where it's very easy to go in one direction, very hard to go in the other direction. And that really falls into 2 key sets of algorithms: factoring of large integers and elliptic curve functions, or the discrete logarithm problem. More recent ciphers that are using discrete logarithms using elliptic curves, you'll often find those referred to with the letters EC. You'll see the letters EC cropping up all over the place in TLS configuration. The other major difference between ciphers is whether they're symmetric or asymmetric. And this is something we've only actually relatively recently been able to have. For the last 2,000 years, essentially, all ciphers are symmetric. You have to have the same key to encrypt and to decrypt. The advantage of these ciphers is they're really, really fast and they're quite simple. But you have this perennial problem of how do you transfer the key? You can't encrypt the key because then the person at the other end can't read it. So it means then that you've got to convey the key by some other means to the other end. And this is why there were things like code books and the Enigma machine with their elaborate mechanism of changing the code, the keys that they were using each day and so on. This has been a problem for millennia, literally. Asymmetric ciphers completely get around that problem by allowing you to transfer a key effectively in plain sight without them actually being able to use it against you. Now, the problem with asymmetric ciphers is that the ones that we found so far are extremely slow. They are multiple orders of magnitude slower than symmetric ciphers. However, what you can do, of course, is use an asymmetric cipher to transfer a symmetric cipher key and then switch to using the symmetric cipher. And that's exactly what happens with TLS. And it also gets used in PGP and SSH as well. It's all the same kind of mechanism. So there's a whole bunch of algorithms of ciphers, older ones like RC4 and triple DES. AES, the Advanced Encryption Standard, is originally the American military thing, but that's essentially the most popular one that you get nowadays. Now, AES used to be really slow because it was all implemented in software. However, Intel added instructions to their CPU's instruction set to provide hardware acceleration for AES. So if you're on a CPU that has hardware acceleration, AES is super fast. CHR20 is a much newer one, and that's really fast in software. So if you're running it on things like old hardware, low power hardware, things like Raspberry Pis and so on, CHR20 will probably give you better performance than AES. Key exchange. Now, the thing I mentioned about using asymmetric ciphers, key exchange is pretty much the only thing that asymmetric ciphers are worth using for. It's really about the only practical use of asymmetric encryption because it allows you to switch to using nice, fast, symmetric ciphers. And again, there's a whole bunch of algorithms related to these. And the most important of these really is Diffie-Hellman Key Exchange. And again, you'll see that referred to in lots of documentation, and you'll see the letters DH. But there are some more recent ones, X25519 and X448. And again, you'll see the EC for elliptic curves used for the key exchange asymmetric ciphers, and also this term ephemeral. Now, if you take all these letters together, you end up with these odd little sequences. This last one that I've highlighted here, ECDHE, is elliptic curve Diffie-Hellman ephemeral key exchange. And so that's a useful designator that tells you what kind of key exchange it's doing. In that case, this is a good one. We want to use that. We like seeing that. These numbers that appear in some of these names, like X25519, some of these refer to prime numbers. I'm not sure about 448. I can't remember where that's from. But the 25519 comes from a prime number, which is 2 to the power of 255 minus 19, which is apparently a prime number. Now, I mentioned that TLS came out in 2018. So what actually changed in it? Well, you saw that there was that long history of SSL and TLS versions. Now, the problem with those is that some of the things that were in there were really terrible. TLS 1.2 even has a null cipher, which does nothing at all. Whatever you put into it just comes out the other end. It does nothing whatsoever. It's just a simple copy. Now, the problem is that somebody calling code expecting their data to be encrypted might have it somehow tricked into using this null cipher, and the data ends up not being encrypted at all. That's exactly the kind of thing that TLS 1.3 wanted to get away from. So it got rid of all of the weak and legacy algorithms and extensions that were in earlier versions of TLS. It was a big cleanup exercise and really pushing forward to try and make sure that essentially you couldn't do things wrong. libsodium, if you've looked at that as well, that takes an even more extreme version of this this approach to things, of just simply not giving you access and not allowing you to change things that might actually allow you to make a mess of it. Because some of this cryptography stuff is really complicated and difficult to understand, and it's very easy for people to make the wrong choices. Given a list of these weird acronyms for the names of ciphers, it's very hard to tell, if you're not familiar with them, which one's the one you should use. So the idea is that take the choice away from them, only offer ones that are actually good. The other thing that TLS 1.3 does is more encryption. It starts its encryption earlier on in the whole process of establishing a secure connection. And that process of establishing a connection is called a handshake, and we'll get on to how that works. And it has lower overhead compared to earlier versions of TLS. All the ciphers support something called forward secrecy, which is a very useful feature. That means that if somebody captures all of your traffic and then later on gets hold of your private key, without forward secrecy, they would be able to retrospectively go and decrypt all of your traffic. With forward secrecy, they wouldn't be able to decrypt it even if they got hold of your private key. So that's a very useful property to have. The elliptic curve ciphers were available in TLS 1.2, but they were optional. Now they're a standard in 1.3. And it also has downgrade protection. One of the most common attacks on TLS connections is trying to trick, if you've got when the connection is initially started between a client and a server, it provides things like a list of which ciphers it supports, but that's done in the clear and there's no encryption at that point. And so it's possible for a man in the middle to try and fiddle with this list and try and trick them into using a lower specification or a weaker cipher for the connection. But if you have a 1.3 client talking to a 1.3 server, the way that this happens is protected against that kind of attack. It reveals the fact that they are both using 1.3. And the thing is with 1.3, as the first thing says here, all the weak stuff has been removed. So there are no weak things left. If both ends can do TLS 1.3, there are no weak options. So you're protected against it using the downgrade protection. So what is this handshake thing? Well, it's actually a relatively straightforward process. It's actually quite a lot simpler than it was in earlier versions. The first thing that happens is the client comes along. This is someone we've never seen before. They say, hi, I'd like to establish a secure connection, please. Here's my key, and here's the list of ciphers that I support. That gets sent to the server. The server receives that and responds with a server hello message, which contains the cipher suite that it chose off the list. So it's the server that's chosen in this case. A copy of the server's key. It also includes the certificate for the server and a signature for it to verify that it is actually really them that's responding and not somebody that's pretending to be them. And then it says, we've finished, and it sends a response back to the client. The client then says, okay, I've now finished. And at the same time as that, can issue an HTTP request with it. So the server then retrieves the HTTP response and gives us our result. Now, this means that it's only taken a single additional round trip in order to establish a secure connection to transfer our HTTP request over. And that's pretty cool. In TLS 1.3, it actually had a whole additional round trip in order to do this. So several steps were combined on both client and server sides in order to allow us to save this thing. And just that simple change has meant like at least a 30% saving in latency in the time it takes to establish the connection. But we're not establishing a connection the same from scratch every time. Having done this, figuring out which ciphers to use, the next time we do it, we know what we can use because we've talked to this server before and we're still the same client. And so it's possible to resume a session. Now this means you still start with the client hello, but instead of giving the cipher suite list, you actually include something called a session ticket. There are two ways of essentially storing the information about how the TLS session is set up. They're called session tickets and session IDs. With the session ID, the information about what the client settings are and what ciphers to use and so on are stored on the server. And the client is given an ID that points at it, so that when the next time it requests something, it goes, oh, my session ID is this, and then the server looks up the configuration for it, and it can then immediately pick up the right cipher settings. Now, the problem with that is it's not scalable. Because it's on the server has to have a potentially infinite storage capacity to cope with all those sessions. Session tickets work in a completely different way. They store the data on the client, but it's encrypted by the server and has a signature on it as well. So the client can't examine its contents and can't tamper with it without detection. So the next time it makes the connection, it just includes the session ticket and the server that can then decrypt it because it encrypted it. So it doesn't, the client never has to see inside it. And it can then just immediately use all the same settings as it did when it initially set the connection up. And the big payoff for this is that it doesn't have to do all that faffing about establishing what to do, and it can get straight on with issuing an HTTP GET. So that gets sent off to the server. The server, hello, comes back again saying, yeah, here's my key again, I've finished, here's the HTTP response, all bundled up together. And that means that we've got 0 round trip overhead on an encrypted connection. That's a really pretty big win. That's really TLS 1.3's headline story. There's no longer a network performance penalty for using encryption. But there is one little caveat here. You notice that I said HTTP GET and not just an HTTP request. And the reason for that is that there's a slight security concern here. There's a potential for what are called replay attacks. If you imagine that somebody's sitting in between the client and the server, they can't read the data because it's all encrypted, but they can still capture it and possibly re-inject it back into the network to try and trick the server into executing the same request over again. And this is a replay attack. But if we look at it from the kind of the typical REST perspective, an HTTP GET should be idempotent. It shouldn't cause a change in state on the server. So no matter how many times you issue it, it shouldn't cause a change on the server. So that means that we're effectively safe against replay attacks. However, HTTP GET requests get abused a lot and people do change state on the server. So you need to be slightly careful about that. If you have a request that's not idempotent, then the fallback is that you would go back to the original setup overhead for setting things up. However, bear in mind that TLS 1.3 starting from scratch is as good as 1.2's resumption process. So TLS 1.3's worst case is as good as TLS 1.2's best case. But there we go. I mentioned this Diffie-Hellman Key Exchange. This is a really neat thing that was actually invented by 3 people, Whitfield Diffie, Martin Hellman, and Philip Merkel of Merkle Trees, I believe. And the 3 of them came up with this mechanism. There's a really nice diagram on Wikipedia, which I adapted for this talk. And this is kind of roughly how it works. And it uses colors instead of keys as an analogy, which works reasonably well. So we've got our 2 protagonists here, Alice and Bob. Now, each of those has a secret color, and this is effectively their private key, which is something they keep to themselves. Now then, in public, visible to everybody, they pick this, a random color. Now, this is effectively the forward secrecy element of this. They don't use their private key by itself. They mix it in with another random number, but they both use the same one. But it's very important that they only ever use that once. It's what's called known as a nonce, a number used once. So they then mix those 2 together, each of them separately, and they each then end up with a different color. And the idea behind this analogy is that unmixing these colors is very difficult. Mixing them is easy, unmixing them very hard. So those colors can then be exchanged in public. And so each of them has a copy of the other's color now, and that's all cool. And then they mix back in their secret colors again. And the net result is they have this combination of the 3 colors, the 2 private ones and the shared random number, but they've each ended up having this common secret, which is effectively the key for a symmetric cipher. This is a really neat mechanism. It's just such a nice little trick. And of course, this is just an analogy. It's nothing really to do with colors. There's a mathematical bit of trickery behind this that means that this is all safe and it just works beautifully. Because the secret key was never transmitted over the network. So even somebody who could see everything that was going on still can't figure out that common secret because the private keys are never exposed. I mentioned in that server hello response that we get when we first connect to a server, it included a certificate. And the certificate is a thing which says that this is a thing that establishes the authenticity of the server, that says, this is who I am, and I'm going to provide a signature to prove it. So how do we actually go about making one of these things? Well, this is how we used to do it. The first thing you have to do is create a public and private key pair. And if you're using RSA, you want to make sure that's at least 2048 bits. Though it's quite common to use 4096 these days. And if you're using ECC, elliptic curve ciphers, then you'll want something smaller. Generally speaking, ECC algorithms are much stronger for their bit length than traditional things like RSA. You then use that to create a certificate signing request, and this includes things like the domain that you're actually issuing the certificate for, and you need to sign that to prove that it really is, it hasn't been corrupted in transit or anything. And then you need to get that signed in order to create an actual public certificate. Now, you can sign that yourself, and that produces something known as a self-signed key. And the thing is that you can issue a certificate to anybody and sign it yourself. You know, you can create an apple.com or a twitter.com certificate and sign it, and it's all cool. But of course, nobody will trust it. And so it doesn't actually gain you terribly much. But self-signed certificates are actually useful. And in fact, all the root certificates, which we'll get to in a bit, are self-signed certificates. It's just that they're self-signed certificates that we have specifically chosen to trust. And that means that those root certificates are held somewhere privately, and they can be used to sign these things by these certificate authorities. And the net result is a public certificate signed by somebody that is trusted fairly universally. Now, all of this is really quite a faff. And a few years ago, Mozilla and some other people got together and produced a certificate authority, which typically would have charged for this, to actually do certificate signing free of charge. And their project is called Let's Encrypt. And it wasn't just the CA, they also produced this thing called the ACME protocol, which allows you to automate all of these steps. So you're going to automate issuing, renewing, and installing certificates, and it's all for free. And it's a huge improvement over the way they used to have to do stuff, and much, much simpler. So how do we know that we can trust these certificates? Well, browsers and operating systems have a certificate store, and these are typically pre-installed on the machine when you buy it, and they get updated through your normal software update mechanism. And so this store contains a whole bunch of root CA certificates. Now, these are the public parts of these things, so they're signed by their private key, and they can be verified by this public part. And then a server that you connect to, or say if you're setting up a certificate for your own site on your server, that has a certificate store, and that's typically somewhere like etc/SSL. And you get your site from the CA and you install it on your server, and that's where it is. But we haven't established trust yet. Now, because the private keys of CAs are extremely precious things and have to be very well protected, they tend not to actually sign the site certificates that they issue directly. They instead sign them using an intermediate certificate. So your site certificate is served by an intermediate certificate. But again, that's still on your server. But then the intermediate certificate is signed by a root certificate, which is available already on the client. Now, it's possible for an intermediate certificate in particular to be signed by more than one root certificate. And this means that if you have a browser that only has one or the other of those root CA certificates installed, it will still work, because it doesn't matter which one vouches for it so long as one of them does. And this is actually exactly what Let's Encrypt did in their early days. They had what's called cross-sign certificates from multiple other already trusted root CAs. Now, you can actually update these things outside your operating system's update mechanisms. And there are two ways of doing that, really. One is that you can go to the curl website and just simply download the latest root certificate bundle yourself and install it. And most web servers, Apache, Nginx, and so on, allow you to just point them in their configuration at a new CA certificate bundle file. But you can also do it from inside apps. So for example, Scott Osizewski has a package called Certainty for PHP that allows you to do exactly that kind of mechanism of updating a bundle, but from inside your application. But this isn't really the end of the story as far as being able to verify a certificate. What happens if, the signature by that root certificate, all that says is that at the time that the certificate was issued, we trusted it. But what if something's happened since then? So say you've done something dumb, like accidentally push your private key to GitHub. This is the kind of thing that people do. So you might then want to revoke it, but then how does a browser find out if a certificate has been revoked? So typically the browser makes a request to the server and it gets a response, which contains the information about the certificate, of course. And so then what can happen is that the browser can ask the certificate authority using a protocol called OCSP, the Online Certificate Status Protocol. So that means the browser makes a second connection to the CA and gets a response. So it gets your response from your server, and then it goes and checks with the CA that your certificate is still valid. But there's a problem here. There's more than one problem here. Your site is now dependent on the CA site. What happens if the CA site goes down? Suddenly, they can't actually be sure that you are who you say you are. They're not verifying the certificate for you. There's another problem. The CA becomes a privacy leak. The CA is very probably issuing multiple certificates for lots of different sites, and these sites might be visited by the same browser. Of course, you only find out about the ones that visit your site, but the CA finds out about all of the sites that this browser visits. And that means that they're in a position to be able to build profiles of things. This is not a good situation from a privacy point of view, and we want to try and come up with a way that's better than this. Fortunately, there is one that's more or less the same, but just with a slight change in architecture. And the trick is that you get your server to ask the CA in advance. So before the browser has come along, we go and request the CA to give us a proof of validity of the certificate. And then when a browser does come along, we attach or staple that proof of validity to the certificate. And then when the browser comes along, we give it to the browser alongside the certificate we've got. So then we've got not only our certificate with our signature, but we've also got evidence from the CA that's, say, within the last 24 hours that guarantees that that certificate is still valid. And you might think, yeah, but surely we could just fake it. Well, no, you can't, because it's signed by the CA, and the CA signature can be verified by the root certificates that you've already got in your browser. So that's pretty cool. There's another mechanism for checking the validity of certificates called CRLs, which is certificate revocation lists. Now, these are very much on the wane. And the idea here is that a browser every now and again goes and downloads a list of all the certificates in the world that have been revoked. Now, as you might imagine, there are quite a lot of them, and it's slow and it's difficult to maintain and generates additional traffic, and it's unreliable, and you know the update rate might be insufficiently fast because the files got too big and so on. So OCSP is really much better than CRLs from that point of view. However, CRLs are still really popular on things like internal corporate networks, where they issue and revoke certificates on a higher frequency basis, but those are certificates that are actually just deployed internally, because there's nothing preventing something like a big company actually establishing their own CA purely for their own internal use. So they sign their own certificates and install those certificates on all their employees' browsers, and that's all fine. So now we're actually going to deploy this stuff. How, or what kind of things you need to think about? The first thing really is use TLS by default. These days, there is really no reason not to. There used to be maybe CPU load concerns, but these days CPUs are so fast, it's really completely negligible. And the fact that it allows you to use HTTP2 just makes things, it pays for itself very quickly. It also simplifies things. You don't have to worry about insecure connections. You can just use TLS for everything. So encrypt all the things. Don't use protocol relative URLs. That's kind of inviting things to attempt to use insecure things by accident. They also don't work very well offline, and they don't work in email. You want to avoid mixing modes. So if you have an HTML page that loads some images, if you deliver the HTML page over HTTPS, but the image might be referred to an insecure site, this is known as mixed mode, and you really want to avoid that as well. Fortunately, there are some HTTP headers that we can use to tweak how that works and automatically upgrade those to secure requests. But if you can't do it, perhaps you're using some legacy CDN or something that you're tied to, you can create proxies on your own service to allow you to proxy something securely. Your cookies, the only one that's really strictly relevant to TLS is the secure flag, but you should really look at setting the HTTP only and same site flags as well, as they provide additional defense against cross-site scripting and cross-site request forgery as well. Now, all of these settings can get quite complicated, but fortunately, millions of people have had to do this before, and Mozilla has this thing here, which is a SSL config generator. So you go onto that and you specify which kind of web server you're using and what level of encryption and what your audience will tolerate, and it will just generate you a config file which basically which ticks all the boxes. The other thing you need to make sure that you do on your own site is redirect to the secure site. So whenever you get a request coming in for an insecure resource, redirect to the secure version of it. You need to use SNI and SAN to host multiple domains on a single IP. Back in the old days, before SNI and SAN, it used to be that you had to have a separate IP for every secure domain that you were hosting. And that ended up consuming IP addresses, and with IP version 4 running out, that's a problem. And it was also a major problem for people doing things like very large scale virtual hosting. SNI is a change in TLS that means that the domain that is being requested actually appears within the TLS request. And this means that it can choose the right certificate to verify your connection against during the TLS handshake rather than afterwards, which is how it worked beforehand. SAN is an additional thing that you can put in certificates called server alternate name, and this allows you to put multiple host names within a single certificate. So those two together just allows you to have essentially as many domains as you like hosted on a single IP, all using different or shared certificates. You can set up the Diffie-Hellman parameters. This helps with the forward secrecy thing. By default, the Diffie-Hellman parameters will typically use some standard values, but you can generate your own, and that's something that OpenSSL will help out with. You want to make sure you use at least TLS 1.2. In fact, as of last month, TLS 1 and 1.1 have been essentially removed from all the major browsers. Enable TLS session caching, so we want to be able to try and make use of those, session resumption, so getting the payoff, especially when we're using HTTP 2. And staple your CA certificates for OCSP. That's something that you do have to configure on your server to make it work. So there are other things that we can do. I mentioned a couple of headers before. This is really the most important one, HTTP Strict Transport Security, HSTS. And this essentially says, we always encrypt. So this is a way of saying that when somebody visits your site, they hit the insecure site, the URL first, and then get redirected to the secure one, at which point they're exposed to this strict transport security header, and your browser remembers that, and the next time you visit that site, it goes, this site uses HSTS, so we're going to immediately go to the secure version. Now, the fact that it still has to hit the site insecurely first is known as a trust on first use, or TOFU problem. And that's something that's addressed by something called preloading, where you can actually add your domain to a list of domains that gets built into browsers and updated periodically by them automatically, a bit like CRLs in some way. But this is in a positive direction and means that if your domain's in the preload list, then the browser will never visit an insecure URL on your domain. You can specify a thing called a Certificate Authority Authorization, or CAA record, and that means that you permit only specific certificate authorities to issue certificates for you. So that means that you can restrict your domain to only allow certificates to be issued by, say, Let's Encrypt or Komodo or VeriSign or whoever it is that you're using. Content security policy header. There's a whole conference talk on multiple conference talks available on just that subject alone. It's a very big and complicated header, but fundamentally it allows you to restrict the sources, and including in particular limiting the page to only loading resources from secure sources. The expect CT header, this is yet another way of authenticating certificates. When a CA issues a certificate, it posts the fact that it has done so into an online log, and anybody can go and inspect that log. You can do it yourself to go and see if this CA did in fact issue this certificate. And if you set this header, it means that the browser should go and check that and refuse to talk to your site if it can't find it in the certificate transparency log. So now we want to, having done all this complicated config, we want to make sure it actually works. How do we do that? Well, the easiest thing is to click the padlock in your browser. and that will give you all kinds of useful information. It'll tell you about the certificate chain, all the signatures, the ciphers that were used in your connection, the hash functions, the MAC functions, whether it's still valid and so on. All of this information, it's all right there in every browser. You can test it on a command line with OpenSSL, provides a function called sclient. Sclient's pretty flexible. You can talk to things other than HTTPS, so you can test things like SMTP as well. The OpenSSL command line tool does all kinds of things. You can do all the stuff that I listed that we now hand off to Acme. So you can generate keys, verify signatures, encrypt files, test connections, generate Diffie-Hellman parameters, and lots of other things. This website, I'll show you a picture of this in a bit. This is really popular as a way of testing TLS configurations. You go to this site and you put in your host name, and it goes and conducts a whole raft of tests on it and gives you a rating and highlights any problems that you might have. If you want to get your domain into that preload list I mentioned for HSTS, you can go to this site and just submit your domain, and they'll check that your site's configured correctly to allow it, and then add it to the list. And there are a whole bunch of other tools to allow you to go and test all kinds of different things. And the last of these is particularly interesting, actually, the web call. I'll show you the output of that in a sec. So this is what things look like when you scan your site with securityheaders.io. This is one of my sites, and you can see that we're getting a nice A+ rating because we've set all of these particular things. Now, this is actually quite an old one. This is, I took this screenshot in 2016, but we still get an A+. However, the public key pins header has now disappeared, and quite rightly too, because it was horribly dangerous. It was possible to lock people out of your site for multiple months by accident. That's not something you wanted to do, so that's gone, fortunately. The Qualys Labs tests come out with something like this, and again, this is on one of my sites, which is of course served with IP version 6, like everybody should be doing these days. And you can see here it gives some top line things. So it's pointing out that we're using a TLS 1.3 connection. We've got an HSTS header set with a long duration, and we also have a CAA record set in our DNS. And this one is from the web call service. Now, this one is pitched at a slightly higher level and is actually more about the privacy rather than the security. And in particular, it tells you about cookies and third-party requests. And it's nice to have those being 0. So what happens, what difference does it make to your site if you actually deploy all this stuff? How can we look at it at a low level and see what difference it's made? Well, this is an example from a conference site that I've been to a few times. Great conference, not such a great website. It's very old, to be fair. Okay, so you can see the very first thing that happens here, that's step 1. It doesn't have a padlock next to it. So this is what happens. So it does a DNS lookup to find out where to connect to, and then it makes a connection to it, and it's immediately kicked off with a 301. So this is the secure redirect. So it's going from the insecure site to the second one, which is just going to be like their index.php or something. And here you can see that it's got the little pink section of that second row. That pink section is the TLS handshake. So it takes a little while to set that up, and then it actually delivers the contents of that. Now, it supports something called pipelining, so you can see the next 2 requests just follow on from that one using the same connection. But then you can see it establishes a whole bunch of other connections. And these ones are all for resources on the same server, but you can see that it's establishing additional connections and doing additional TLS handshakes on top of those things. And what this tells us is that it's using HTTP 1.1, which opens multiple separate connections to transfer multiple items at the same time. It's faster than just using one, but it means you have all this overhead. Next up, we've got a couple more that happen. We've got some more DNS lookups and some more TLS connections for external CDNs that we're using. Now, overall though, you can see that our total page load time is around 2 seconds, which is quite slow. And there's quite a lot of overhead in this that's really on top of all the other stuff that's actually being transferred, all the HTML, all the images, all the JavaScript, and so on. So this is what happens when you do it right, the new way. So this is one of my sites again. So you can see we do a DNS lookup, we do a connect, but notice this first step is straight in there with HTTPS. We've skipped the whole insecure request completely because this site is in the preload list. The other thing is, this is using a TLS 1.3 connection, and look at the size of that little TLS connection there. It's tiny. The TLS, establishing the TLS handshake, doing the TLS handshake takes around, what, a quarter of the time it takes to do a DNS lookup. That's really very quick. And in fact, looking at the stats for it, that took 26 milliseconds, which is, that's great. We're perfectly happy with that kind of result. The next thing you notice is that we're loading all these other resources, but there are no additional TLS connections. There are no DNS lookups, no additional connection overhead. It just loads the other stuff straight away. And this is because we're using HTTP2, capitalizing on the TLS connection. And the net result is that the page has finished loading at 0.7 seconds, which is actually before the previous example had actually loaded its first byte. So we're complete before it's even started. So that's really, a lot of that is down to just configuring TLS and getting it configured the right way. So to summarize, it can be free. It's faster if you use HTTP2, or because it allows you to do it. Use it everywhere by default. Take additional simple measures to maximize security through headers and so on. Help Hansel and Gretel make it to your site safely. And of course, they all lived happily ever after, and that's the end. But except, of course, it's not really the end, because security is not something that you can do and then forget about it. It's an ongoing process that requires constant vigilance, constant updating, tweaking of parameters and so on. And all that stuff is tiring for humans, but easy for computers. So you need to automate this stuff as much as possible. But there's plenty of other conference talks on that. Anyway, thank you very much. And that's all from me. Feedback on joined in, please. I've stuck my speaker deck link in the chat earlier as well. You can email me, and I'm also on Twitter as me and my alter ego. And you can find me on GitHub and Stack Exchange as well. So here we go.
Brilliant. Thank you ever so much. That was a fantastic talk. If anyone has any questions, pop them in the Q&A tab. I do have one question. Well, what happens, or maybe it's never happened, but what happens if a CA's private key gets compromised or leaked or anything like that? Has that happened?
Yes, it has. And in fact, worse things happen. Entire CAs have been taken down. And they often actually misbehave. There are quite a lot of CAs that are actually quite dodgy. In fact, Let's Encrypt ran into a really quite a major problem fairly recently. It was just 2 or 3 months ago, I think. And they had to revoke and reissue maybe something like 20 million certificates.
Oh, wow.
And because it's Let's Encrypt, and everybody that's using Let's Encrypt is using Acme and Acme clients of one kind or another, it meant that for the most part, this all happened reasonably automatically and wasn't actually that much of a pain. So this is the big payoff for using things like Acme. There's actually, like, the classic counterexample is Ericsson did something a couple of years ago. Well, no, actually they did something a long time ago that only came to light a couple of years ago. And in the UK, Vodafone's network was using switches made by Ericsson. And suddenly, in the same second, every single one of these Ericsson boxes stopped working. And it took down something like 2/3 of the whole of the Vodafone network in the UK. And it turned out the reason for this is that Ericsson couldn't face the idea of trying to update the TLS certificates. So they built the TLS certificates that were in the firmware on their routers for the mobile phone network had 10-year lifetimes. But 10 years later, they were still being used. And so they all expired at the same second.
It's like a millennium bug.
That was just terrible. But obviously they were paying attention fairly rapidly after that, and managed to deploy a new certificate to them all. But yeah, there's plenty of scope for things to go wrong in quite major ways. And the classic thing is people forgetting to renew certificates. And Google's done it, Apple's done it, Microsoft's done it. On like major public services, it's like someone's just forgotten to renew a certificate. And that's something that the Acme and whole Let's Encrypt thing has really helped with. because the ACME protocol applies to any service, any DNS, any CA can use it, but it's most commonly associated with Let's Encrypt, because Let's Encrypt's certificates only last for 3 months, and that means that you have to renew them much more often. Now, this gives a security advantage, because it's yet another means of not allowing bad certificates to hang around for too long. But at the same time, it means you really have to be on top of renewing them. But the whole thing with the ACME protocol is that it makes that really quite straightforward.
Wow. Incredible.
Yeah. So I think we've got some questions here. TLS state has improved on a number of things. However, say I wanted to set up a new e-commerce website, should I be implementing TLS 1.3? Is it fully compatible with all browsers? Yes, it is. In fact, TLS, as I mentioned, TLS 1.3 had a long and difficult gestation. There were several draft versions, and all the browsers was just kind of in lockstep. As soon as a new version came out, they all implemented it. And the take-up was really, really rapid. It got into all the browsers very quickly. But the other thing is that just because you have implemented TLS 1.3 doesn't mean that you can't also offer other TLS versions. It's just that it's a compromise. But these days, really, you shouldn't be offering anything less than TLS 1.2, and it's possible to configure TLS 1.2 really pretty strictly. The determining factor of how strictly you configure it is really down to knowing your audience. So, for example, if you're doing like an API backend for an iOS application, Apple's update rate on operating system versions on their iOS devices is incredibly high, and so you can impose really very strict, very up-to-date settings for those things. But on the other hand, if you're doing something that's used by people on corporate Windows networks that have been around for decades, the chances are there's going to be somebody trying to access your site using Windows XP and wondering why it doesn't work. And the only way of doing that is allowing some horrific old settings, which are potentially a compromise for everybody else. So it really depends on your audience, how tightly you can nail down your TLS config. I hope that answered that one. Somebody, Jonathan Jeffries, saying, hi Marcus, I use PHP Apache's Docker image. I spent quite a while trying to configure HTTP2, but it seems it isn't possible with the version of Apache that's included. I've used Apache with TLS 1.3 and HTTP2 without too much difficulty. Now, I don't remember the exact version that added HTTP2 support, but it's several years ago now, at least 4 or 5 years, I think, since HTTP2 came around. So I mean, it was definitely it's in one of the Apache 2.4s, but I couldn't remember exactly which one. But it's old now, and I've got sites that run on Apache. I mostly use Nginx, but I've got some that are using Apache, and there's no problem with HTTP2 there. In fact, there are some things that Apache does very slightly better than Nginx, but on the whole, I prefer Nginx. It's smaller and faster, and I prefer the config. That's just me. So I think you need to look a bit harder. That's the answer to that one.
Brilliant. Thank you ever so much.